Hello, welcome to this lecture on chemical process modeling and simulation. In the previous lectures, you got an introduction to the different types of problems that chemical engineers tackle in their career and got an introduction to how mathematical modeling plays a significant role in helping the chemical engineers tackle their problems. And then in the next second lecture, you got an introduction to what modeling is all about, what are the different types of models, how modeling plays a role in daily life. We looked at different examples through which we understood that. In this lecture, we are going to see what is mathematical modeling and what are the different types of mathematical models, and we will see a practical example of mathematical model. So the lecture, I'm going to start with a mathematical model that I had put up in the previous lecture, which is the mathematical model of a crude distillation unit. And this is the model equations for a crude distillation unit, atmospheric crude distillation unit at the Indian Oil Corporation's Mathura refinery in India, Mathura in India. And we have the component material balance equations, liquid and vapor summation equations, enthalpy or energy balance equations, and equilibrium relations. This is for any ith stage of the CDU or the crude distillation unit. J denotes, the subscript J denotes the various components. Okay, so there are n stages, I going from 1 to n, and C components, J going from 1 to C. Well, so we saw a mathematical model like this. So what do these mathematical models represent? Mathematical models are approximate mathematical representations of processes occurring in a unit or a set of units. So if you are writing a mathematical model for a single unit, like for example, the atmospheric crude distillation unit. So this set of equations that we saw there represent, of course, mathematically, because these are equations, the processes that are occurring in that atmospheric crude distillation unit. What is the process, basic process that occurs in the CDU? It is one of distillation, where the low volatile component is volatilized and moves upward from bottom of the unit to the top of the unit, and that is predominantly in the vapor phase. And the heavy components, which are predominantly in the liquid phase, flow down. The heavy volatile components, the less volatile components, rather the heavy components, they condense from the vapor phase and they get collected, accumulated in the liquid phase, and they keep coming down. And as with any crude distillation unit, there are multiple products. So at different intermediate stages, there are products that are removed, and then there are additionally side strippers. When the product's liquid stream is removed, there is a mini small distillation column in itself, where there is there's further enrichment of the product that is basically to be collected from that stream, and then the remaining part of it is sent back to the column. So there are multiple side strippers, and there are what are called pump arounds to ensure basically some liquid is taken from a lower stage and then pumped back up to a higher stage, which, even though sort of overrides any separation that is achieved, that has been achieved by the liquid coming down, it is now being put back up, right? And that separation is lost. However, it ensures that there is sufficient amount of liquid in all the stages, and also it's sort of in distillation processes such as that of crudes, since no product is a pure component, they are all cuts, right? So it ensures that there is sufficient amount of the distribution of the various components that are present in a cut by its pump arounds. So all these are there, and the equations were written that essentially captured all these processes. So essentially, the flow of the vapor up the column, the flow of the liquid down the column, the equimolar or non-equimolar counter diffusion that takes place between the vapor and the liquid phases in each stage, and then there may be some sort of a stream coming in due to a pump around, or going out or coming in due to a side stripper, and the various product streams that are exited at different stages. There is a feed that comes in at a feed stage. All this are all processes that take place, number one. And number two, in addition, this mass transfer process goes to a point where the hope, the idea that the stage is designed to reach as close to an equilibrium between the vapor and liquid phases as possible. And this equilibrium is established in the thermal sense. The temperature is essentially equal. That's a very good approximation. Mechanically also, it is a very good approximation that the vapor and the liquid phases are in almost the same pressure. Chemical equilibrium, not a whole lot. I mean, yes, there would be some stage efficiency. You want to maximize that stage efficiency as much as possible. And so in all of these manners, we are writing equilibrium relations. They are not necessarily fully met in the unit, and therefore those are approximations. And therefore when we write that there is the total mass is conserved, the species are conserved, and the energy is conserved, yes, they are conserved, the conservation is exact, but we partition the total energy into those assigned to different streams. We say that the vapor stream leaving the tray has a certain enthalpy, the liquid stream leaving the tray has a certain enthalpy, the vapor stream entering the tray has a certain enthalpy, the liquid stream entering the tray has a certain enthalpy. This distribution of the total energy, that is of the content that is present in the system, that distribution is approximate because we don't exactly know the local variations in temperatures, local variations in pressures, local variations in compositions, and therefore there is approximations that come in even into those conservation equations in the way we assign numbers to them. Okay, so yes, there is approximation. Mathematical representation, yes, all kinds of equations that you saw there, right? And then that's the mathematical model. It's an approximate mathematical representation of a set of processes that occur in a unit or a set of units. We can look at various examples. You have studied so many units and processes in your chemical engineering courses so far, and all of them you have described mathematically. This basically means that mathematical expression is also an approximation. For example, you consider first order reaction in a CSTR. That the reaction is first order, that the kinetics is first order, is an approximation. That the tank is perfectly mixed flow, an ideal CSTR, or even if you say there is non-ideality, the extent of non-ideality that you are able to capture is an approximation. So approximate mathematical representations of a processes occurring in a unit. A distillation of a multi-component mixture in a tray tower column of equilibrium stages at trace. We just discussed this. Heat transfer in a shell and tube heat exchanger in a countercurrent flow. Well, again, the countercurrent idea is an approximation. And you assume that the flow is plug flow because you usually have a velocity, constant velocity that you assign to the hot stream and the cold stream. That's an approximation. And the heat transfer coefficient is an approximate measurement, right? And therefore the correlations that you use for your Nusselt number and Reynolds number, Prandtl number, with which you sort of design these exchanges, approximations, the geometry approximation, and so on and so forth, but you capture all that behavior using some mathematical representations. Filtration of a slurry in a plate and frame filter press. One of the most common approximations that you will make is that the filter cake has a certain uniform porosity, which of course is not true, right? And the slurry that is coming in has a uniform dispersion of the solid particles, which of course is not true, right? But within those approximations, you write mathematical representations. You write something like a Darcy's law and so on and so forth. So there you are, again, approximate representation of some real process. Chemical vapor deposition of a graphene or carbon nanotube. This is something that we will discuss, whether we discuss it for graphene or for some other processes like semiconductor fab, like silicon deposition or something like that. All right, we will take up one CVD example as a model at some point. I will discuss this in more detail. I just wanted to put an example of something that is more sophisticated, uh, recent sort of process development. Spreading of a virus during a pandemic. I mean, this whole thing, this whole lectures are being recorded at the time that we are all going through a corona COVID-19 virus pandemic. And how does this virus spread? And there are all kinds of predictions that are going around, which are all based on mathematical models, and there are lots of approximations that go into those models. So the types of mathematical model depends on the nature of the process. So depending on the nature of the process, you can characterize a model to be either a deterministic model or a stochastic model. A stochastic model is a model that allows for fluctuations in variables. It allows for random fluctuations in variables, and therefore the model involves random variables, whereas deterministic models involve absolutely determinable certain variables with no scope for fluctuations. It's basically the kind of assumption that you make. So you look at a process, the same CSTR. If you look at it as an ideal CSTR, the model that you develop is a deterministic model, whereas the moment you start talking about residence time distribution and there is a non-ideality in the CSTR and you want to capture it, the whole model becomes a stochastic model. Nature of the variables also, and yes, this of course the example that I gave you now is with the CSTR is one of is one of a certain process that is deterministic or stochastic, in the sense that the path traced by the fluid particles in a CSTR, right, when they from the time they enter to the time they leave, that path traced, that flow process is a stochastic process, and therefore that is captured by a stochastic variable which you define to be the residence time of that particular fluid particle, and then you look at the residence time distribution of all the particles that you collect at the exit. So nature of the process, nature of the variable, and depending on the purpose of the modeling, so you can either have a descriptive model or a prescriptive model. And a descriptive model is one of process identification. We will try and take up one example of process identification model at some point in this course. But a prescriptive model is what we typically usually come up with, where you can predict. Prescriptive models can they have some sort of a predictive power, and therefore you can use those models to make decisions, use those models to optimize. On the other hand, descriptive model is a model that is developed to identify the nature of the process. What are the different types of mathematical representations? Yeah, you can write equations, which is what we saw. Sometimes you can have inequalities. This was something that we saw in the first lecture when we were looking at some sort of constraints on what can be the outlet temperature or inlet temperature to a reactor, inlet composition of an inert species into a reactor, especially when the reactor has recycle and so on and so forth. This temperature cannot be greater than 150 degrees, or your inert composition cannot exceed 1 mole percent or 2 mole percent or whatever it is. So those are all inequalities. And then you can also represent, multi, sort of a large process of multiple units as graphs. And this graphs, I'm not talking about the graph that describes, a graphical way of describing what is the relationship between one variable and another variable. That is also a graph. But I'm talking about these various nodes and edges that connect each other, and then they form a certain shape, right? So those kind of graphs can also be used in mathematical representations. If you are looking at equations, you can have either linear algebraic equations or nonlinear algebraic equations, single equation or a system of equation. Linear ordinary differential equation, nonlinear ordinary differential equations are systems of such ordinary differential equations, systems of partial differential equations, inequality constraints, as I was saying, in optimization problems. And systems of a mixture of these equations, basically some algebraic equation and some ordinary differential equation. Nonlinear algebraic equation, nonlinear partial differential equations. So these are all basically differential algebraic equations, that is DAE, or integral differential equations. You can even have integral equations, all right. When you have your RTD, your concentration, exit concentration is given by a convolution integral, right, of the E distribution, which is your residence time distribution. That is, multiply that with, that is the probability distribution, and then multiply it with your concentration of that particular fluid particle at the inlet, and then you integrate over various times from the inlet to outlet. So you get basically an integral equation for the exit concentration. You can have some equations that are differential equations and some equations that are integral equations, and therefore you can have integral differential. But given all of these equations, what is the goal of a mathematical model? What is the ultimate purpose of writing mathematical models? So the purpose of mathematical model is to establish a relationship between the inputs to the system and the outputs from the system. This could be singular or plural, doesn't matter, inputs, outputs, right? So you want to be able to express some form of a relationship, either a direct relationship or an indirect relationship. Either you write, y is equal to ax plus b, that's a direct relationship between y and x. An indirect relationship is to say that dy by dx equal to ax plus bx square. So you have to integrate that equation to get the direct relationship. So therefore basically so you want to establish some form of a relationship between the inputs to the system and the outputs from the system. And so here I want to talk about the central idea in developing mathematical models. Okay, so here is the mathematical model of a unit or a process. There is a box at the center, and this picture we will see repeatedly. All right, there are some inputs that go into the model. There are some outputs that come from the model, and then there are so you have some variables that describe the process that takes place in a unit which you are trying to model. So let me rephrase this. The mathematical model is an approximate mathematical representation of the various processes that occur in a single unit or a set of units, right? So there are variables that describe the process. For example, you are talking about a chemical reaction. At what temperature is this reaction taking place? At what pressure is this reaction taking place? What is the rate constant for this chemical reaction? What is the order of this chemical reaction? These are all process variables. And what about the unit variables? Where is this reaction taking place in a CSTR? So what is the volume of the CSTR? If it is a PFR, what is the cross-sectional area and what is the length? And what are the input variables? What is the inlet concentration? What is the temperature? What is the pressure of the input stream? And what about the outputs variable? What is the outlet concentration? Which means, of course, you can calculate what is the outlet conversion, right, from that CSTR or PFR or whatever unit. All right, and what is the temperature, what is the pressure, what is the flow rate of the output stream? And then the mathematical model itself becomes some form of a relationship between all these variables, and they are expressed as constraints on the unit or the process. So okay, so you basically specify, for example, in one way of solving a CSTR problem, you would have done this. You specify the volume of the reactor and you ask what is the output concentration or what is the conversion from the CSTR. So basically you can specify the constraint on a unit and constraint on a process. You say that the rate constant is given by this value, okay, or some expression which is a function of temperature, and you have your input stream, and then you have your unit process variables that are given. Volume is given, temperature is given, at which the reaction take place is given, and then calculate the conversion. Or you can have, for example, your conversion is given, tell me what should be the volume of the CSTR to achieve that conversion. You've done all these kinds of problems. So ultimately, to solve such problems, you need to have these constraints or these equations. They could be equations, they could be inequalities, equality or inequality constraints, different types of equations that we just saw in a couple of slides ago, right? So this basic framework is how you can envision any mathematical model. So the moment you are asked to model any system, you should first ask yourself, what are all the inputs that go into the unit or a process? All right, or rather I should back up and say this. The moment you are asked to develop a mathematical model for some process or processes that are taking place in one unit or a system of units, you have to ask yourself, what are all the inputs that go into that unit or the systems of units? And you should ask yourself, what are all the outputs that come out of that unit or the system of units? And you have to then ask yourselves, what are all the variables that I can use to describe that unit or system of units? And what are all the variables I can use to describe the processes that take place in that unit or system of units? Once you've defined all these variables, then you start looking at what sort of constraints, equations, or inequalities that relate these variables. And then you simplify that, you get a mathematical model which you simulate or solve. All right, so this sort of a systematic approach we will take in this course. And the core idea is therefore that whole systematic approach is therefore distilled in this block diagram that describes how mathematical modeling works. So here is what you aim at. Ideally you would like to see output as a function of the various input stream variables, the unit variables and process variables. Sometimes you will be asked to calculate the unit variables given a certain output. So you may have to invert this function in some form or the other. But this is what happens. This is the sort of goal of a mathematical model, to express a relationship like this. Now, to close the lecture, I'm going to give one example of modeling, and that is pertinent to what is happening right now, where we are facing a pandemic of corona COVID-19 virus. How does this virus spread in a city? And I want to understand this. There has been a recent study whose reference is given to you in this in the reference below. And based on that study, I'm not going to show any of the equations here, but I'm going to show the block diagram, so to speak. So basically, what are the outputs that you are looking at? What is the total number of infections? What is the number of active infections? How many of these active infections are hospitalized? How many of the total infections have recovered? And how many of the total infectious patients have unfortunately passed away? So these are the kind of information that you want to learn and track. All right, this is what the model should be able to predict. These are the outputs. What is the input? Who are all the susceptible people? Who are all the exposed people? Out of these exposed people, how many have become infectious and are exhibiting symptoms of COVID-19? How many have become infectious but are not asymptomatic? And then, as we have seen, there are these class of people simply by their virtue of their profession or their travel history and whatnot. All right, they become inadvertently exposed. They become super spreaders, right? There was this example of how an outbreak happened in a large market, and then people just picked up goods wholesale, and they went and sold at different places, and they transmitted the virus completely unintentionally. But they did end up becoming super spreaders. So one person ended up exposing a whole lot of people compared to what would have happened if that person's profession were not that particular profession. So we have to account for such cases of super spreaders also. So these are all the inputs, and using these inputs you want to predict these outputs. And for that you have to understand some sort of unit variable and process variables. What are the unit variables in a given city? What is the population demographics? You also have to know the population density, where the population density distribution, which areas are sparsely populated, which areas are densely populated, and so on and so forth. And how is the city planning? What is the way in which these population is going to come and interact with each other? What is the healthcare infrastructure? What is the administrative infrastructure? What is the police security infrastructure? What are the jobs and employment infrastructure? What kind of jobs are available? See, I was just talking about the supermarket, So if this place is like one major place where a large number of such agricultural produce or other produce is sold, and then it's a manufacturing hub or whatever it is. So there will be these kind of concentrations through which such super spreading could emerge, right? And what is the shopping infrastructure, and how much of the shopping infrastructure is working, how it is working? All of this is going to determine how susceptible people could get exposed, become infectious, symptomatic or asymptomatic, and then how super spreaders could emerge, and in turn this will you know determine at any point in time in the city the total number of infections, the number of active infections, and so on and so forth, right? So what are all the constraints? What are all the constraints that we are looking at? The constraints that we are looking at is, okay, so what kind of contact exists between people? Direct contact or indirect contact? What is the extent of physical distancing that is being observed in the community? What kind of hygiene and social behavior is observed in the community? What kind of gatherings take place, and what are the potential for super spreading? What kind of hospitalization is taking place? Are the infectious people, if at all, especially when they are symptomatic, are they getting hospitalized? What is the general immunity in this society? And that plays a major role. There seems to be a big difference worldwide if you look at it. Some countries seem to be surprisingly more capable of resisting this virus. Why? If something may be discovered much later, but that is a reality today that we are facing. And what are the comorbidities for the people who are susceptible, who are exposed, who are infectious, that could cause the people to become symptomatic, and for those symptomatic people to become very serious to the point that recovery may not be possible and fatalities may occur. So all of these are constraints. So we have to have ways to express each of this mathematically speaking, right? And then find a way to develop a set of equations that relate the output. I want to know total infections as a function of all these three. The ones in the purple font on the left side, the brown font at the top, the red fonts at the bottom, all of these. How does the number of recoveries depend on the number of susceptible people, number of exposed people, number of symptomatic infectious people, and so on and so forth? How does the number of recoveries depend on population demographics, job and employment infrastructure, police security infrastructure, obviously healthcare infrastructure? How does the number of recovery depend on the percentage hospitalization, the nature of immunities, the nature of comorbidities, and so on and so forth? So there has to be some sort of equations that will have to be developed for all of these. That would be the model, mathematical model for predicting. This would be a prescriptive predictive model that describes that predicts how the COVID-19 coronavirus is likely to spread in any given city. And this paper that is cited below is an example, is a very good example of how such a model could be developed. All right. So this is the kind of mathematical modeling that we are trying to learn, of course, with respect to chemical engineering systems in this course. So if you have any questions, you may please post those questions in the comment section below. And I hope you are able to understand how mathematical models are constructed, what are all the various pieces in the puzzle, how they work in achieving certain specific goals in terms of either describing a system or predicting how a system will behave, and using which you can take decisions. You can have mathematical models that can be used as decisions. The decisions themselves can be expressed mathematically, and so on and so forth, right? So with this, I would like to thank you for listening to this lecture. Please give your feedback, and looking forward to interacting with you in the next lecture. Thank you very much.